Awesome. So, ISIM labs. So Brian Story just handed you this lab to do, and it's like 2 in the morning. You really don't want to walk up all the way to the lab, so you decide you just want to simulate it in LTspice. So you look at the lab, and he's having you run through 2 RC filters. I mean, we've all seen an RC filter before, and he's trying to make you do a 2 filters in a row, which should theoretically give you twice the filtering capacity. So it should filter it like instead of like slope of -1, for example, it'll be a slope of -2 after the cutoff frequency. So that's what we should expect. So at this point, you should open up LTspice. If you did it through Wine at this point, then also, if you have any questions, I can't see everyone's face, so feel free to just like stop me, just start talking, and I'll make sure to slow down to get your question. Cool, so open up LTspice. You're gonna notice that it looks like it was designed in the 90s and never progressed from there. That is very true. That is due to the fact that it's a very solid piece of software and it's free, so no one ever puts any time or energy into the user interface. And that's just the fact of life. Cool, so you're gonna open up a new schematic. I highly recommend to go into Tools, Control Panel, Drafting Options, and then modify the hotkeys. Please, please, please modify the hotkeys. These are the hotkeys that I use for when I use LTspice. They're very similar to that of KiCad. So if you use KiCad, it'll be a bit more familiar. When you just install LTspice, all of these will be function keys. So to do things like moving, setting a line, deleting stuff, it's all a function key. And I feel like for me, it was more helpful to like make my own hotkey. So I'd recommend doing that the first thing. Cool. Excuse me. So for the sake of this presentation, I'll try to use the buttons up top as much as I can, or I'll tell you which hotkey I'm pressing. The hotkeys that it starts out with is R for resistor, C for capacitor, L for inductor. Very basic. The rest of them are function keys for the few exceptions. So let's look at the lab. Wrong screen. Sweet. Let's look at the lab, and we'll see that we need to do 2 RC filters in a row. Okay. I'm going to use my own values for this presentation, but we know that there's 2 RC values in a row. So you're going to hit R to set a resistor down. Control R rotates it. That's already built in. Then you hit C for a capacitor, and you set it down. I highly recommend putting them in line. It'll make your life a lot easier when you're setting down the wire. Sweet. And at this point, we need to give them values. I found it to be very useful to set the values as parameter or as like a variable name, which we'll define later in under a parameter command. So to do that, you do open bracket. Let's do uppercase R, lowercase f, close bracket. There you go. And then for the capacitor, same thing, open bracket, uppercase C, lowercase f. What you put in there is completely arbitrary. I'm just using RF and CF for resistor filter and capacitor filter. Lovely. But you want 2 of these in a row, right? So what you're going to do is you're going to come up here and do copy. So copy, click and drag, and at this point you'll have a set. Put this back in line, and sweet, now you have your resistors and your capacitors down. Let's wire that all together. So there's a little wire thing up here, hit wire, and this is cool about LTspice. You can just click on the left and then drag all through these components, and voila, they're all wired together. Cool, so looking at the schematic, there is a ground. So we need to make sure we ground our capacitors. Sweet. So hit G for ground. This is, again, already built in. Set your ground points down. Sweet. We've done that. Now we need to define our variables. Okay, so LTspice can be run either as a graphical user interface the way we're doing it now, or you could also run it under the command line. So you could actually like make your schematic through like on a text file and then have LTspice interpret that, and it'll run through commands for you. So everything is, all the commands are text-based. So you go here on the top right, hit spice directive, come with a little screen. So in order to define your variables, you want to do dot param. So dot param defines the parameters of the system. So in this case, we're going to do RF equals, no spaces here, In this case, I chose my own values to get to a 10 kilohertz low pass filter. So R equals 795.77, CF equals, and this is where I think it's pretty cool. So LTspice interprets units. So if you were to write down 20 and F, it'll interpret that the nanofarads as N as 10 to the negative ninth power, which is kind of cool.
Question, where did you find the edit text thing?
That's a great question. So I'm going to hit enter. You find it on the top right here where it says .op. I don't know, can you see my mouse? It's right. So you click that, and it you can either set a comment down, so like nothing fancy there, just a comment, font size, and so forth, or you can do a spice directive. It doesn't tell you a list of spice directives, so you kind of need to do some Googling to figure out what you need to do, or look into the help file, which is also, it's up here, help, and then help topics. That can be useful, but it can be a little clunky to figure out how to use it. So I recommend just Googling it. So yeah, sweet. So we have our circuit, we have the variables defined. What this means is all of the RFs will be of value 795.77 ohms, and all of the capacitors will be of 20 nanofarads. Sweet. But we need a voltage source, right? We need some input to the system that's going to be causing some output, right? So what you want to do is come up here, and you see the logic gate looking thing right here, which says component next to the hand and the diode. You want to click that. And here is a list of the components that you can use to put in. There's quite the variety, and you'll find everything from voltage source to current source to op amps and a bunch of other components. LTspice, what it stands for, this is a good time. LT is Linear Technologies. That was the company that first created the software. Now, Linear Technologies was acquired by Analog Devices. So the website will be under Analog's website. And SPICE means simulation program with integrated circuit emphasis. There are other SPICE programs you can find out there, like PSpice is one of them, but they either cost money or they're a bit more convoluted, like less easy to use. And LTspice gets updated basically every couple of years at this point. And it's really easy to use, like relatively easy to use compared to the other ones. So that's why a lot of people use it. Cool. So we're going to select a symbol. In this case, we're looking for a voltage source. I know from using this that, so you can type in voltage, and here you'll find your voltage source. I just put VO. Oh, let me see this. Cool. Voltage. Wonderful. So click that, bring it over here. So what we're going to do is make a Bode plot of this. If y'all recall from ISIM, a Bode plot is you're looking at the frequency response of your circuit. What that means is you're trying to see what the output is versus the input of a specific circuit. In this case, we're doing a filter. So it's going to be sending an AC wave of varying levels of frequency to the input of your circuit, and then you're going to measure the output and compare them together. So you'll see an amplification factor as well as a phase offset. Today, we're going to be focusing on the amplification factor, which is usually denoted in dBs. You really don't need to know what dBs are at this moment, but it's basically a ratio of output to input between the two. Cool. So you set your voltage source down. At this point, you're going to want to right-click it. So here you can set a DC value for it and a series resistance. We want to do something a bit more advanced than that. So we're going to hit advanced. And here you have a bunch of options. At this point, I know for a Bode plot, having searched it up and done it myself, you want an AC amplitude of non-zero. So we're just going to put 1 here on the right side. Small signal AC analysis, AC amplitude 1. You do have a bunch of options here on the left you can do to play with your circuit. I would recommend in your free time looking at what each one of these does. Some make more sense than others, like intuitively, like a sine creates a sine wave, but what's PWL? Like, I don't know what that stands for, but I'm sure Google could help you there. Cool. So AC amplitude of 1, okay. Sweet. So we have to make sure we also ground this because it needs to be in the same reference as your filters here. So hit G for ground, put that together, come up here, hit the wire at the top, and then wire your circuit together. Sweet. So now we have our voltage source, our two filters, and let's, for clarity, set the output. Let's set a net label like you do in KiCad to the output of this filter. So up here, you're going to look at label net. It's to the right of the wire and to the left of the component. Well, this is ground and that's resistor. So label net. And then let's just call this filter 1. So you can set those wherever you want. You can set in the middle of the circuit. You can set at the end of the circuit. We're going to set at the end for this. Cool. So let's look around. We have our voltage source, we have our filter down, and we have our net label. Sweet. We're good to go. At this point, you can enter if you know off the top of your head, I do not, what all of the run commands are, you could just type it in yourself into the Spice operative, or you can hit run and it'll prompt you. Run is on the top left. It's a little guy that's running. Yes, it's very cheesy. And it'll prompt you with the simulation window, like telling you like the different ways you can simulate. You can run the simulation. So we're going to do AC analysis here. AC analysis just means that we're making like a Bodhi plot. We're looking at the small signal analysis of the filter. So cool. We're going to do a decade, which means that decade is like a every like 10th order of 10 was what we're doing here. You probably saw this in ISIM where the x-axis is a log axis where it's orders of 10, and we're going to be doing that type of frequency analysis. So we want to sample nth number of points every order of magnitude. So with like power of 10. So here we're going to put just 100 points per decade. You can do more, you can do less, depending on resolution, how complicated your filter is, and so forth. So we're going to do here, we're going to start frequency at 1 hertz, and we're going to go all the way up to a megahertz. So you can do, actually, you can just do 1e to the 6. Sweet. E6 is just a shorthand for 1 times 10 raised to the power of 6. E is just a shorthand for it. LTspice supports it. You're going to also do E negative 6, which is 10 to the negative 6 power, which is going to be 0.000001, I think. But we're going to go up in frequency. Cool. So this spits out a little command line here for it to interpret. You don't really matter what order you put these in. If they're on the screen, it's going to run it. Cool. So now that you've done all that, I'm going to take a quick pause for any questions.
When you set the parameters, why do you put nanofarads for the capacitance but no units for resistance?
That's a great question. You don't actually have to put the F part. That's just for my sake. It would also work just as fine if you put 20N or 20e to the negative, I think 9. So yeah, it's just for me being able to read it easier. It doesn't actually affect the models at all because it recognizes that it's for a capacitor, so it'll be doing it in the unit for a capacitor, which is farads. Great question.
Gotcha. Thanks.
So unnecessary but helpful. Any other questions?
Yeah, every time you run a command, does it just like print or like appear on the screen?
Yeah, great question. So when you hit run, oh darn, when you hit run over here and you already have your command down, it's basically going to run the simulation, and you're going to see this black window pop up. Since the program knows we're doing AC small signal analysis, creating a Bodhi plot. A Bodhi plot is what it gives us. Usually, you're not going to see. If you did other types of analysis, you may not see frequency here on the x-axis. You may see something else. You can read voltages, you can read currents, but it usually will just pop up with the black screen to tell you that the simulation is done. If it's a really, really complicated circuit, or it has to do like a lot more computation because it's a very like the math to solve it isn't very straightforward, then sometimes it'll take a long time to run it. I have simulated some circuits where it's taking like 5 to 10 minutes to run something, and then at the bottom left you'll see it like running through the different math and so forth. Did that answer your question?
I was just mainly curious about like why there's this like dot param at the bottom and like the dot AC.
Yeah, so the dot followed by some word are directives for the LTspice, so it tells it to do something. In this case, it can be including a library for a component. .ac is specifically to run a simulation on it. The order that you put these doesn't really matter on the screen. I recommend putting them next to each other for the sake of clarity, but all they're doing is basically informing LTspice of something about your circuit, something for it to know. If we didn't put param down, it wouldn't know what RF and CF stand for. So it'd be looking for it, but it would show you a warning saying, hello, RF and CF are undefined. What should we do about that? So at that point, you should usually stop the simulation and you define them. Sorry, did that answer your question?
Yeah.
Cool. Sweet. So at this point, we have set a circuit down, put our voltage source, and simulated it. So now we can start probing around the circuit. You're gonna notice that if you hit escape to let go of any tool you're using, your cursor, and when it's right above filter 1, looks like a little crosshair. When you put that over different parts, you can read the voltage or read the status at those different parts. So you see the little symbol, it means the current running through a component, and the red little probe is for reading the voltage there. In this case, we want to read the Bodhi plot at filter 1. So we're going to click on filter 1, and then you get something like this. This looks like roughly what a second order filter should look like. On the right hand side, again, we're going to neglect phase shift for today. So just hit right click on that. My cursor's over here on the right, and hit don't plot phase. Cool. So now we're just looking at magnitude. So looking at the ISIM sheet, you can see that, okay, cool. So we did that. And here it says that when we have two series and filters in series, that the amplitude and the phases, amplitude multiplying the phases add. Okay, cool. So the amplitude is defined by this equation here. Okay, cool. Say you wanted to double check your filter off of what you expected. You have a couple options here. You could export the data and plot it in like Python, spreadsheet, or MATLAB or something. Or what I think is particularly neat is LTspice allows you to plot math on top of your plots as they are. So to do this, let's say we wanted to do this equation. We're going to right-click your plot, hit Add Trace, and we're going to do some math. So here in the expressions, it'll plot anything you want. So in this case, we want to plot a function. So going back to this function, 1 over 1 plus RC omega squared, we're going to do 1 over 1 plus open parentheses. LTspice, so I love LTspice for the most part, but it doesn't allow you to pull in your parameter values into this. So you actually need to type these by hand. So in this case, you put 795.77 times 20 nanofarads, which is e to the negative 9, times, it says omega, which means frequency. So we're going to do frequency. And in this case, I know that this function describes it in radians per second as the frequency. So we need to multiply this bottom part by 2 pi to make it hertz. So you do times 2 times 3.14, close parentheses, squared, close parentheses. Cool. So this function defines, it's going to plot this function, and it's this function that you wanted to plot right here. So theoretically, 2 filters in a row should be this that we're about to see. Cool. So that's interesting. They're a little off. So you can see that the green line here stands for the Bodhi plot of the filter, and the blue line here stands for the theoretical that you should have seen. There's a bit of a difference, and I think that's exactly what Brian's story was trying to get you to see, was that 2 filters in a row placed together like that causes them to couple each other. Couple each other just means that one system is affecting the other system in an unexpected way. So what is actually happening? Well, what's happening is the current through this resistor is actually flowing into both of these capacitors, which is influencing the function that is describing the way the filter is working. In this case, it manifests itself into a cutoff frequency slightly before where you expected it. And you might be wondering, like, okay, Corey, so our low pass filter cut off a bit lower than we expected. Isn't that fine if we're making a low pass filter? Yes, in this case, you could argue that, but you don't want your circuits doing things that you can't predict accurately. Because in this case, it might manifest itself as a lower cutoff frequency, but in other cases, you might not be able to predict what that is going, like what the coupling of two filters or coupling of multiple systems may do to each other. So you want to avoid that as much as possible. And the way you can do it using what ISIM has taught you is an opamp. So an opamp will make sure that the current between the two filters are decoupled, but the voltage is not. Because the thing that we're concerned about here is the voltage waveform flowing between the two filters. So in order to quickly see what that looks like, we can copy this filter. So let's go up here and hit copy. Does anybody have any questions while I do this? Cool. So copy the filter, pull it up, and then we're going to make a bit of space for the op amp. So you want to use the move little hand that's open, kind of like Spock. Sweet. So you want to move, select the R and the C, drag those over. Sweet. And now we want to add an op amp. So the way we do that is we go up here and go under a component. And then if you look to your left, you can see op amp is a category of components. In this case, you'll click that, scroll all the way to the right, expand this a little bit, and we're just gonna use op amp here. Like your ideal op amp, you don't have to worry about your voltage rails. It's a very basic model. Notice that in the comments here, it also says ideal single pole operation amplifier, you must opamp.sub. I think it's supposed to say you must include, but it doesn't quite say it there. But I'll show you what that is. So you hit OK, put this op amp here. Cool. So let's wire this together. And as we know that a unity gain follower op amp means that the non-inverting input, the positive input, goes into the input of the signal. And then you're going to want to create a feedback loop by putting the inverting output and wiring that to your output. So doing some wires there, wonderful. But before we can run this, oh, and we also need to make sure we connect the input of the filter to the voltage source. Sweet. Let's make sure we name this differently so they don't overlap the net labels. So right click the net label, hit filter 2. Sweet. And we need to include the op amp. So to do that, you go as a spice directive on the top right, and you hit .include opamp.sub. So you're including the subcircuit op amp into the simulation, is what you're doing here. If you end up taking circuits with Brad, you're going to have to include his special library that he's made for class. So you're going to end up using this at some point. If you decide to import a component that's not already in the LTspice library, you'll have to include that component. Some manufacturers will include a spice model for their components so you can more accurately model what's going to happen if you're using that very specific component. So we're just going to hit OK and just set this down somewhere. Sweet. So now we can run the simulation again on the top left, hit run. Sweet, and I think we're good to go. So we hit filter 2, and notice how the filter 2 is now directly above our theoretical line for what the filter should have been. If you click on the blue, the blue here represents the function that you put in, and it sets a cursor down. We don't really care about the cursor at the moment, but I'm just trying to highlight the line itself. So if you hit blue, it'll highlight the line, and if you hit the red, you'll also see the red line. They're directly on top of each other, which is why you can't see both at the same time. So now the filter is acting the way you expected. What you needed to do was decouple the two filters from each other. So now we get the actual filtering capacity we expected. The cutoff frequency happens where we intended it to be, which was 10 kilohertz, which is right here. So we can just pull this over. Boom, 10 kilohertz. On the top, on the bottom right here, if you ever heard a cursor, it shows you what is going on. Like it shows you the magnitude, the phase, and everything you need at that point, or it'll show you the voltage at that point. You can do some math with it as well. Before I continue, does anybody have any questions about anything I've done so far?
Can you type in that dialog to move the cursor?
Yes, you can. That's a great question. So if I'm going to click this right here, you can type in here like frequency exactly. Oh, shit. Oh, I guess not. That's lame. I thought you could. Nope, you cannot do that. I take it back. I lied to you. Sorry about that. I think you might be able to do that if you do a different type of analysis. I don't understand why it's not letting me do it now. Anyway, that's a great question. Do we have are there other questions?
Yeah, so if you have multiple circuits in the drafting field below, can you simulate one at a time or multiple of them at the same time?
If you have them down here?
Yes.
Yeah, so it'll simulate them everything at the same time. What you could do is just, if you really wanted to, you could disconnect. So this little scissors button, hit cut. You can cut this wire and not simulate the top one. It's because there's no input to it. And you can just simulate the bottom one. But yeah, anything that's plugged in together to a voltage source or something that the simulation can affect, it will affect it and it will simulate it.
Okay, got it. Cool, thank you.
If you had like two voltage sources though, like just two separate circuits, could you simulate them both at the same time?
Yeah, so you're saying that if you had like this guy over here and we cut the wire and it was connected?
Yeah, basically.
I think you can. That'd be a weird niche case, but I think you probably can. You could set as many voltage sources as you want down, and you could type in commands for them to run those at different differently if you'd like. I have had circuits where I've had like 4 voltage sources. One is like a 5-volt rail, one is like a reference rail, another one doing the thing that I wanted to change over time. So you can have as many as you want, but if you wanted to simulate 2 distinctly different circuits, you probably just want to use 2 different schematics in that case. Sweet. If you have any more questions, feel free to interrupt me. The last thing I'm going to touch on are LC filters. So the thing, like RC filters are good at what they do, low pass filtering, but it's the limitation there is they're really good at filtering signals that don't have a lot of power, as in like a lot of current flowing through it. So let's say that you wanted to provide a low pass filter for something that was powering electronics, right? Say like a buck converter, like the one that Adi taught about last week. You probably noticed that he used a different type of filter, and what he ended up using was an LC filter. The reason for that has to do with the fact that your losses in a circuit, like one of the biggest losses in a circuit is when you have a lot of current running through some resistance. So that's going to create heat in the real world. So you don't want, let's say you're designing a buck converter that was outputting 5 amps. You don't want 5 amps running through a resistor, to power your load. In this case, the resistor value is almost 800 ohms. That's a lot of heat, assuming you put 5 amps through it, or if you had 5 amps on the other side. That is unnecessary losses that you could avoid by using a better filter. In this case, you could use an LC filter. So we're going to simulate a quick LC filter. Inductor is L. Control R to rotate. So we'll put this right there. C for the capacitor. Put it down right there. I know you can do some math to figure out what the value should be, but I already did that ahead of time. So the inductor, I'm just going to define it here. Should be 12.67 millihenries. I'll put e to -3. And your capacitance, I did 20 nanofarads as well, or I guess, yeah, 20 e -9. Again, so we'll make sure we ground our capacitor. Let's put wires. Oops. I accidentally ran the simulation and it wasn't happy about that. Wires through. And then we're going to set a wire out here for us to read the output. If you don't put a net label, it also, I'll show you, like, it actually runs it just fine, but the name that it comes out on your plot isn't super clear on what it is. So now that we have our LC filter down, we can run it. So we hit run. Now we have our little screen here. Let's read the filter from filter 2, and let's also read the output of this filter. I'm going to eliminate the phase. Cool. So here we see that the cutoff frequency is exactly at 10 kilohertz again, but something interesting is happening. In this case, what's happening here is that this is the resonating frequency of this filter, which means that at this frequency, the denominator of whatever function that's describing this approaches 0, which means that the overall function amplitude approaches infinity. In real life, this doesn't really happen. It's not quite possible. So there's one thing about this model that we're not capturing well, which is the, it's called the ESR of your inductor, which stands for equivalent series resistance. So all inductors, and fun fact, all capacitors too, have some equivalent series resistance to them. So we'll see that if you right click your inductor for your model, and it'll give you a couple options here. It'll give you the peak current, so the current at which the inductor saturates. It has too much energy. It's hosting too much energy to the point where it can no longer hold more. You can also modify the series resistance. So in this case, let's do something outrageous, like 500 milliohms, right? So 0.5 ohms in the series resistance. So we're gonna hit OK, and we're gonna run it again. Oh no, that's disappointing. Let's do 2 ohms. Okay, so the peak is actually getting smaller. It used to be at 80 dB, and now it's at a different value. If we put this series resistance to something like 10 ohms, for example, you're going to see the peak slowly come down, -40. Oops. If you want to highlight a single net, for example, all you need to do is double click that net and it'll get rid of the rest of them. So now we have that. Right click again, 100 ohms. And you can see that the resistance is actually making the peak go a lot further down. It's flattening it out, but we still have a second order filter akin to your 2 RC filters in a row with an op amp. But in this case, the inductor can handle a lot more current and it's a lot less lossier. It's a lot more efficient at allowing that power to flow through it. And that's exactly the type of filter that you want for any type of power electronics, which is why you use an LT's filter and buck converters. Any questions about what I said? This is the end of my presentation. I hope you all learned a bit about how to use LTspice and how to simulate filters, do body plots. Yeah, any questions?
Is there a way to put current on the plot, or is it just voltage only?
So you could see the current flowing through your inductor. It's a little weird for this one because it's a Bode plot, so you'll be looking at the magnitude of the current flowing through it. So like if you click this, you'll see the current, but it's a little weird. Like that I don't know myself quite how to make sense of what this means for the current flow, like a current Bode plot of it. Regularly, if you're doing other types of simulation, like let's say that you wanted to look at how your circuit handles varying levels of current or voltage or current if you wanted to. So in that case, you'll be doing a different type of analysis. If you right click the line that runs your simulation here, so AC, DEC, right? If you right click that, you can see the different types of simulation you can do. You could do a transient simulation, which means that you're looking at the steady state, or rather like you can imagine that like what does a circuit look like if you're like over time between like 0 and like 10 seconds, for example, right? Then you can look at the current and the voltage of your entire circuit between 0 and 10 seconds of whatever you decided to simulate. So yes, in other types of simulation you can, but not, it makes less sense for this Bode plot to look at current. Did that answer your question?
Yeah, thanks.
Cool. Any other questions?
Why was 500 milliohms an absurd equivalent series resistance value for your inductor?
That's a great question. If you're using an inductor to filter a powered signal, then having 100 ohms as your ESR for your inductor is the same thing as having a resistance in the series with the inductor of 100 ohms. In that case, you're going to have a lot of losses. You're going to have I squared R of whatever current is flowing through, like that much. That's how much power you're going to be losing through that inductor with 100 ohms alone, which is why 100 is absurd. The values are actually the values that you'll actually see more likely is going to be on the order of milliohms. So anywhere from like 5.00.005, yeah, 5 milliohms to maybe even, actually this is 50. Oh my God, I'm really bad at math. I'm sorry. To hundreds of milliohms. 1,000 milliohms is a single ohm, and you probably don't want even that. Like that's still quite a bit. So yeah, that's why 100 ohms would be absurd, like literally illogical for the amount of ESR you're going to see in an inductor. I hope you never buy it, at least.
Sure.
Yeah, great question. Other questions?
Yeah, why don't we just always use inductor capacitor filter rather than a resistor capacitor filter?
That's a great question. Inductors can be, like price-wise, inductors can be more expensive, and they're also a lot larger. So like the inductor is a coil of copper, right? Wrapped around something. It could be air or like iron or something else, like some type of core. And that just physically takes up more space than a resistor does. So that could be one reason why you would rather use that. Sometimes you don't need it to be, like sometimes your signal isn't going to have a lot of current, so you can't justify that much space if you don't actually need to filter, like if you're not filtering power, for example. So which is why you can use a basic RC filter for your low pass filters, like requirements. Does that make sense? It all comes down to space and cost. Sweet. I hope y'all find some time to, what is that? I gotcha. I hope y'all find some time to run through this yourselves in LTspice. If you have any questions, feel free to reach out. I might do more LTspice tutorials in the future to help run y'all through the steps of what it's like to perhaps simulate a circuit on the car that you're unfamiliar with. But yeah, thank you for coming. I hope you learned something new today.